Let others also join, then we'll start the session in a few minutes. Okay, so welcome everyone. Let's start our session. So welcome to the week 6 of the tutorial of thermodynamics. Okay, so I hope you all are regular to your watching the lecture videos taught by the professor as well as on the NPTEL portal, as well as you are thorough with your assignments. Okay, and those who have missed the tutorial sessions, they can watch these sessions on my YouTube channel as well. You all have got a sheet from NPTEL team where all the recording links are there. Okay. So in the previous uh, week 5 tutorial, we had started with basically second law of thermodynamics. Okay. And the last topic in that was Carnot theorem. So we have calculated the efficiency of a Carnot engine. Okay. Basically. So I'll share my screen. I hope my screen is visible. Okay, all right. So today we'll start with discussion of the drawbacks of Carnot cycle, as I told in the towards the end of week 5 tutorial. Okay, so let me write the topic. First of all, the topic is Carnot theorem. So which has basically four processes. So the first process was isentropic compression from 1 to 2 stages, then isothermal heat addition, then isentropic expansion, and isothermal heat rejection. In detail, we have discussed in the last tutorial. And the efficiency formula for that, we got Carnot was 1 minus T lower by T higher. Also, we plotted the TS plot, temperature entropy plot, and the pressure volume plot. Okay. So we can get the work area under the pressure volume plot gives us the work basically. And that was quite a narrow region. Okay. So let's start with the discussion of the Carnot drawbacks of the Carnot cycle. So let me write. And in today's tutorial, we are going to do a lot of questions. Okay. So first drawback is basically that we assume that all the processes are reversible. And ideally it is okay, but in practical scenario, it is impossible to achieve all the processes to be reversible. So there are some irreversibilities every time. That's why Carnot efficiency was the maximum or reversible efficiency as well. Okay. So first is all processes are considered to be reversible, which is impossible to achieve practically. Okay. Second is, if you see all the four processes, it comprises of two isothermal and two adiabatic or isentropic, you can say reversible adiabatic is isentropic only, processes. And to achieve isothermal condition, process has to be extremely slow to maintain the temperature. We know that, okay? Whereas to have an adiabatic process, the process need to be extremely fast so that there is no heat change happening. Okay. And combination of above two is impossible to achieve in a single cycle. Okay. So there is a cycle running and you are saying that two processes should be very slow and immediately a fast process should happen. Then in the third process, it should be very slow and immediately a fast process should. That is not possible for a practical engine to work. Okay. Second point is it consists of mainly two processes, that is isothermal and adiabatic. Reversible adiabatic is isentropic only, that process. And to achieve isothermal condition, process has to be very I should write extremely slow. Whereas for adiabatic process has to be extremely fast. Okay. And combination of above two is impossible to achieve. Right? Is impossible to achieve. Next is area under the pressure volume curve give us basically our work. Okay, we know that very well. So, but here there is a very narrow region for pressure volume plot. If you have observed the graph which we plotted in the last tutorial, so that was quite a narrow region because adiabatic has a higher slope compared to isothermal. We have discussed this. Okay, gamma times the slope of the isothermal process, because of which the region comes out to be very small. Okay, so that's why the area work obtained is also very less. Okay, that is one of the drawback of Carnot cycle. Third is area under PV, that is pressure volume curve, is having very narrow region as slope of adiabatic is gamma times slope of isothermal. So obtained work net is this. Therefore, work net, or we should write like this. Net work obtained is this. So that's one of the drawback. Okay. So here are few points to note that first is that efficiency of reversible engine is always greater than irreversible engine. Okay. Is always greater than irreversible engine. And in practicality, all the engines are irreversible. And maximum possible efficiency of a reversible engine is given by Carnot only, that we have written here above. Maximum efficiency of reversible engine is given by Carnot. Okay. That is, efficiency of Carnot is 1 minus T lower swing temperature to that of source higher temperature. Okay, which is function of temperature only. Now, there is another point. If there are n numbers of reversible engine operating at between the same temperature limits, T higher and T lower, okay, with different working fluids, then the value of maximum possible efficiency, or you can say Carnot efficiency, is same always. Okay, or you can say idle efficiencies. It is basically an idle efficiency. Okay, so if you have multiple reversible engines operating between same temperature limits, either the fluid inside all of them are different, all the engines are different, still the efficiency of those reversible engines will be the Carnot efficiency, or maximum or reversible efficiency. Okay, so if you have n number of reversible engines, suppose I make a figure, so this is a T higher. Okay, and this is T lower. Okay. And we have suppose engine 1. All of them are reversible engines. Engine 2, engine 3, and so on. Okay. So all of them operating under the same temperature limits, T higher and T lower. If there are n number of reversible engines operating between same temperature limits, with different working fluids, then the value of maximum possible efficiency eta or Carnot efficiency eta is same always, okay, or idle efficiency you can say. Okay, if there are n number of reversible engines with different working fluids are operating between same temperature limits, then the maximum efficiency or Carnot efficiency or idle efficiency all are same. That means Carnot efficiency is independent of the working fluid. So if you see the efficiency formula also, there is no term of any material property. Okay, no working fluid is there, property is there. It's only the function of temperature. Okay, so Carnot efficiency, we can write that. Carnot efficiency is independent of working fluid. Any doubts still here? No doubts? So if it's said, suppose if it is said like this, that efficiency of Carnot is given as 1 minus T lower by T higher is given as 0.55, and efficiency of an actual or irreversible engine is given as what? It is work net to that of Q supplied. How much work you obtained and how much heat you supplied to the system is given to be 0.45. Then what is the efficiency of engine? They have asked. Okay. What is the efficiency of engine? What will you say? If it is said like this, and it's in the same temperature limits, okay? So efficiency of Carnot is higher than the efficiency of actual or irreversible engine. So efficiency of engine is 0.45 or 45%, okay? And if they have specifically asked what is maximum or Carnot or reversible or idle efficiency, then you will say it is 0.55. Okay. But before that, it is always 0.45 only, because actual engines are irreversible in nature. So efficiency of engine is 0.45. Okay. But if they say Carnot, efficiency of Carnot, maximum, idle, or reversible, then it will be 0.55. Okay. So the above engine is irreversible, reversible, or impossible? It is irreversible in nature. Okay, it is irreversible in nature. So first way was to get that you can check through efficiency that your engine is irreversible, reversible, or impossible. One way is you check through the efficiency that your actual efficiency is less than or equal to or greater. It cannot be greater than Carnot. So either it's less than Carnot, actual is less than Carnot, or equal to Carnot. If it's equal to Carnot, then it is reversible engine. If it is less than Carnot, then it is irreversible engine. Okay, so the above engine is the option will be like this: irreversible, or you can say possible. Second, reversible, or you can say ideal. Third, impossible. So our answer is, correct answer is, it's an irreversible or possible engine. It's possible in practical. One way is to check through the efficiency. Another way can be through, you remember that statement in starting of the last tutorial I gave Clausius inequality. That is dq by t, cyclic integral of dq by t is less than 0. Okay, so one way can be for irreversible engine, cyclic integral of dq by t is less than 0. For idle, it is equal to 0, and for impossible, it is greater than 0. All right. Okay, this is the another way. Else you can check through the entropy. If you know what is the entropy of the universe. Okay. First way was this. I'll write the headings. First way is through this. Second way is through entropy. ds of your universe. You know that for irreversible or possible thing, entropy of universe is always greater than 0. Okay. But here for reversible, it is equal to 0. And for impossible, universe is less than 0, which is not possible. Entropy of universe is either 0 or greater than 0. It cannot be less than 0. We have discussed in detail all these things. Third way is your efficiency. Okay, so write that. Efficiency of actual is greater than efficiency of Carnot. Efficiency of actual is equal to efficiency of Carnot. And efficiency of actual is less than efficiency of Carnot, which is not possible. Okay, these are the three ways to get to the point of checking that engine is reversible, irreversible, or whatever. Okay, I think till here there are no doubts, I hope. Okay, then let's come to the questions. Okay, so the first question is that we have done this question earlier also, but now through the concept of entropy, we are discussing second law. So through the concept of entropy, you have to prove this. Prove that PV raised to the power of gamma is constant for reversible adiabatic process. And that time we didn't knew that reversible adiabatic process is also called as isentropic process. Okay, but now we know from after the starting of second law, we know what is reversible adiabatic process. So use the concept, take a hint that use the concept of entropy, TDS equations, and try to solve. So take few minutes, solve it, then we'll head to the next question. Okay, some other student has also joined. So we are doing the proof of this PV ratio or gamma is equal to constant. Okay. Using, and the hint is you have to use TDS equation. I'll just give a minute more and then we'll discuss. Okay, let's discuss now. Pretty simple. We have already discussed this question. So we know that from the TDS equation, we know that TDS is TU plus PdV. We know this equation very well. So it said that the process is adiabatic. Okay, reversible adiabatic. Okay, so that means it's an isentropic process. So for that, entropy ds is 0. So for reversible adiabatic, ds is 0. Okay, so therefore we know that 0 is equal to du plus pdv. Okay, so du can be written as minus of pdv. All right, we know that du internal energy is at constant volume. So cv dt, it can be written like cv dt. dv dt is equal to minus pdv. So we'll say that this is equation 1. This is equation 1. Now another equation we know that TDS equation is TDS th minus vdp. Okay. Again, ds is 0. So it will be 0 minus vdp. Why ds is 0? Because it's reversible adiabatic. So isentropic process. So dh is vdp. Okay. And enthalpy is defined as constant pressure for an ideal gas. So Cp. So in the question it is said that for reversible adiabatic process for ideal gas only. Okay, we are talking. So it's VDP. So let us say this equation is numbered as second. Now we'll divide the equation 2 by 1. The equation 2 by 1. So that is Cp dt is equal to VDP divided by Cv dt minus PdV. Okay, so dt and dt cancels out. Okay, and you know that Cp by Cv is gamma only. This gamma is equal to VDP minus PdV. Rearrange them, transpose. So it is what you can say dP by P plus gamma times dV by V. So let me write like this. Gamma times dV by V is equal to minus dP by P. Transpose this to the left hand side. So that's dP by P plus gamma times dv by v equal to 0. Now you can integrate them. Integrate. What you get? Integration of dp by p plus integration of gamma is a constant value. It can come outside the integration. dv by v is equal to 0. And integration of 0 is constant. So integration of dp by p is ln. So ln p plus gamma times ln v, constant is c. Okay, you can write c or ln c, both means the same. You can write like this: ln p plus ln v to the power of gamma for log is equal to ln c. This is p e raised to the power of gamma is equal to c only. Okay, if you take away the logs. So that is your proof. And see, proved this. Pretty simple question. All right, let's head to the next question. Yes, proof for ideal gas. DSS Cp times dV by V plus Cv times dP by P. Okay, and use this result for adiabatic process to find PV raised by gamma is equal to constant again. Okay, and use, when you prove this, then use this result for reversible adiabatic process to prove PV raised to the gamma is equal to constant. So first prove ds is this relation, and then use this relation to prove again this. Now it's the good question, okay? Good challenging question. Now you have to think. I'll give again few minutes to think on this. All right. Few of you have done. Let us solve it now. Okay, pretty simple question it is. So again, we'll use the TDS equation. So TDS is du plus pdv. We know that. Du can be written as cv dt plus pdv. Okay. Now we know that since from ideal gas PV is equal to RT. So P can be written as P by T can be written as R by V. So ds, take this T on the right hand side. This is CV dt by T plus P by T PV. So put this P by T here. Right. This can be written as CV dt by T plus R dV by. This is your equation number 1. Okay. This is your equation number 1. Similarly, you know that TDS is dH minus VdP. TDS dH minus VdP. So ds can be written as TDS can be written as Cp dt minus VdP. Now again, since you know that PV is equal to RT, so V by T can be written as R by V. Okay, and take this T on the right hand side. So this is Cp dt by T minus V by T dP. So use this V by T, replace through this. Okay, so this can be written as ds Cp dt by T minus R dP by P. This is your equation number 2. Now what you will do, you will multiply the equation number 1 by Cp and multiply equation 2 by Cv, and then you will subtract those equations. Now you multiply equation number 1 by Cp and subtract it from by multiply the equation number 2 with Cp. Okay, so multiply the equation 1 with Cp, multiply equation 2 with Cv, and you subtract both of them. So what will you get? That is, I'll write in very detail. So this is, or let's first write the first process. There is no confusion. Okay, see, multiply Cp with 1. So Cp with 1 is equation 1. Cp ds is Cp Cv dt by T plus R Cp dV by T. Okay, the equation 1 was this. So if you multiplied Cv here, Cp here, you get that equation. Similarly, multiply equation 2 by Cv. Now, and let us name this equation as A, or let us name this equation as 3. Okay, now multiply equation 2 by Cv. So this is Cv ds is Cp Cv dt by T, and that is R Cv dP by P. And this equation is 4. Now you subtract, that is 3 minus 4. Okay, equation 3 and 4. So subtract this 3 and 4. So this term will be Cp Cv. So Cp minus Cv and ds will come out common. This term, if you see, cancels out because these two are exactly the same terms. And this is RCp dV by V, and minus of minus gives plus RCv dP by P. So that was the only thing which we have to prove. And you see, it is Cp minus Cv. Left hand side is this. Right hand side is RCp dV by V plus RCv dP by V. And you know that what we had to prove? ds is Cp dV by V plus Cv dP by P. Okay. So what is Cp minus Cv? Cp minus Cv is R. We have proved this Mayer's equation. So Cp minus Cv is R. So this is R ds R Cp dV by V plus R Cv dP by P, since Cp minus Cv is R. So this R cancels out everywhere. Therefore, our final equation is Cp dV by V plus Cv dP by P. And this was the required thing to prove. Hence proof. This first equation, we had proof now. Okay, I hope there are no doubts. All right, and we have to use this equation to prove PV raised by gamma is equal to constant. Now use this equation. So for reversible adiabatic process, you know that ds is 0. Since for ds is 0. So in above equation put ds is 0. Cp dV by V plus Cv dP by P. What you do? Divide both sides by Cv. Divide by Cv. What you will get? 0 will be 0. Cp by Cv, dV by V plus dP by Cv by Cv is 1 only. Since Cp by Cv is nothing but adiabatic index, that is gamma. So 0 is equal to gamma times dV by V plus dP by P. Okay. Again, you can integrate. So this is integration of dP by P plus gamma is outside the integration, constant value, dV by V is equal to integration of 0. It's the same thing like in previous question. ln P plus gamma time ln V is equal to ln C. So from here, PV raised to the power of gamma is equal to constant. Hence, proved. Okay, it's a very good question. So again, go through this, that what we have done. We have used first the TDS equation. We expanded du as Cv dt. We transposed t on the right hand side and wrote P by T as R by V here, which is from the ideal gas law. Okay, so we got the first equation, ds is equal to this. All right. Now coming to the next equation, TDS is dH minus VdP. Expand dH as Cp dt. Put V by T as, by transposing T on the right hand side, put V by T as R by P. So you got the second equation. All right. Now you multiply the first equation by Cp, you get this third equation. You multiply second equation by Cv, you get the fourth equation. Subtract equation 3 and 4. Okay, get Cp minus Cv is ds into ds as this. And you know that Cp minus Cv is R. Okay, so finally you prove that the first equation which we wanted to prove, ds is equal to Cp dV by V plus Cv dP by P. All right. And now you have to use this equation to prove for reversible adiabatic process for an ideal gas, PV raised by gamma is equal to constant. And we know that ds for an isentropic process, ds is 0. In the above equation, put ds as 0. So what you get? 0 is Cp times dV by V plus Cv times dP by P. You divide by Cv both sides, then you integrate them, and finally you get the PV raised by gamma is equal to constant. I hope it is pretty much clear. No doubts in this question? Very good question. All right, let's come to another question. Cp is given to be, now Cp is not constant. Cp is given as a function of linear function of temperature A times Kt, and Cv is given as B times Kt. Okay, and it is said that Cp and Cv of ideal gas are like this, where A, B, K are the constant. Oh, I should loop it. For ideal gas, where A, B, K are constant. T is the temperature. T is temperature. And you need to prove for reversible adiabatic process, T to the power of B into E to the power of KT into V, that is volume to the power of A minus B, is equal to constant. This is your question to prove. Okay. All right. You have to prove this. Again, take a few minutes to think on this. It's a very good question. Okay. So CPCV are given in terms of temperature, initial linear function of temperature. You need to prove that for reversible ideal gas. Reversible adiabatic process, this expression T to the power of B, E to the power of KT, B to the power of A minus B product is equal to constant. Okay, I think most few of you have done this. All right. So let's discuss the solution to it. It's a very pretty simple question to do. Since it's given that Cp is A plus Kt and Cv is B plus Kt. So you do Cp minus Cv, that is R, you know that. So what is Cp minus Cv? From above equation, A plus Kt minus B plus Kt is equal to R. So Kt and Kt cancels out. So it is A minus B is equal to R. You're left with the Cp. So A minus B is R. Okay. Now you know the equation, since TdS is du plus PdV. Okay, you know this equation. So ds can be written as Cv times dt by T plus P by T dV. And since you know again, P by T can be written as R by V. Put that. So ds is Cv dt by T plus R dV by V. Now you put this R from here to be this. Okay. So this is ds Cv dt by T plus A minus B dV by V. Now you know that for reversible adiabatic process, ds is 0. Since for reversible adiabatic process, ds is 0. 0 is equal to Cv dt by T plus A minus B dV by V. And Cv is given to be B plus Kt. So put this B plus Kt times dt by T plus A minus B dV by V is equal to 0. Okay. Separate the terms. So this is B times dt by T plus K times T by T cancels out. So it's K dt only plus A minus B times dV by V is equal to 0. Okay. Now you can integrate. Integrate. So it's B is constant given in the question. So it's dt by T. K is also constant dt plus A minus B. A and B both are constants outside the integration dV by V is equal to integration of 0. Okay. So dt by d integration is ln B times ln T. Integration of dt is T only. So K times T. Integration of dV by V is ln of V is equal to constant C. Okay. All right. So now if you do take the ln or the other side, you can write, first of all, you can write T to the power of B plus KT plus V to the power, ln times V to the power of A minus B is equal to C. If you do the ln, take the ln on the other side. So it will be T to the power of B, right, into V to the power of A minus B into E to the power of KT. Okay. Is equal to constant, which was required to hence prove. Pretty simple question. All right. Any doubts in this question? So you know that Cp minus Cv is R. R comes out to be A minus B. After putting the values of Cp and Cv, you know this equation TdS is du plus Pdv. On putting the R as A minus B, and after that, you know ds is 0 for reversible adiabatic process. And putting the values of Cv and integrating, opening the brackets and integrating them, you get this expression which is required to be proved. I think no doubt still here. All right. Now let's come to a good question again. New good question. An ideal gas is heated from temperature T1 to T2 at constant volume. Then gas is expanded back to its initial temperature according to law P raised to n is equal to constant. So if entropy change in these two processes are equal, both these two processes, then devise an expression for polytropic index n in PV raised to the power of n in terms of adiabatic index. That is gamma. Right? Pretty good question. So you have two processes. First, ideal gas is heated from temperature T1 to T2 at constant volume, that is isochoric, and then gas is expanded back to its initial temperature using a polytropic law, that is PV raised to power n is equal to constant. And it is said that if entropy change is equal for both of them, both the process, then you need to find an expression or devise an expression of n in terms of gamma. Do this, take few minutes. It's a good question. Okay, I guess few of you have done. Let's discuss the solution to it. All right. All right, let's discuss the solution. So it is said that you have two processes. So first we write the equation of dq is equal to du plus pdv. Okay. Or you can write as TdS is equal to du plus pdv. Okay. So you know that from the TdS equation, it is du plus pdv. Okay. So for process 1, which is a constant volume process, since V is equal to constant for process 1, so it is dv comes out to be 0. So it is du is cv dt and it is tds. Okay. So ds is equal to cv dt by t, and you can integrate 1 to 2 process. Okay. So from 1 to 2, ds cv 1 to 2 dt by t. Okay. What you will write ds, it will be S2 minus entropy at point 2 minus entropy at 1 is equal to Cv ln of T2 by T1. Okay, you got the entropy for the first process. They have said that there are two. Are we connected? Hello. Okay, I think we lost for about a few seconds. Okay, so what I was saying, I'll again repeat the solution. Okay. So first it said that entropy of the two processes are equal. Okay, the entropies are equal, then means we have to compute the entropy. That's a simple thing. Okay, we have to compute the entropy eventually. So if you see the equation TdS is equal to du plus pdv, and process 1 is constant volume process, so V is constant there, so we can say dv is 0. So TdS is eventually cv dt, and transposing this t on the right hand side, ds is equal to cv dt by t. cv dt by t. Now you can integrate from point 1 to point 2 for the first process 1 to 2. So integration of ds, integration of dt by t from 1 to 2 is S2 minus S1 is equal to cv ln times ln t2 by t1. Okay, cv ln t2 by t. All right, clear? Pretty much clear. Now we got the entropy for the first process. Now we need to find the entropy of the second process. Again, we know that TdS is du plus pdv. Okay, so what you can say, take t on the right hand side, and du can be written as cv dt by t plus p dv by t by t dv. Okay, and p by t can be written as r by v, since p by t is r by v for ideal gas. So put this, ds is cv dt by t plus r dv by v. All right, clear? So what you can say, you can integrate now. Integrate for the process from 2 to 3. So first process was 1 to 2, then it's 2 to 3. Okay. So ds 2 to 3 Cv dt by t 2 to 3 plus r 2 to 3 dv by t. Okay. Now, so it can be written as S3 minus S2 is equal to Cv ln T3 by T2. But we know that T3 and T1 are equal because it said in the question it is brought back to initial temperature. From when you are going from 2 to 3 process, the temperature is to the initial temperature. So we can write this as T3 as T1. Okay. Plus R ln V3 by V2. Since it's given that T1 is equal to T3. Okay. Oh, correct. Any doubts in this? So we have the other equation, that is equation B with us. So this was equation A of S2 minus S1. This is equation B of S3 minus S2. Equation B. And this was equation A. All right. We have two equations. Now what will you do? Think. What can be the next process? Those who are not able to do, what can you do in this? I think I've shifted this rod that side. Okay. This is equation B. Nothing for a minute. We have two equations, A and B, using this process. It's given in the question that both the entropies are equal. Okay. Since entropy change, okay, it is said that entropy changes for both processes are equal. That is S2 minus S1 is equal to S3 minus S2. So you can compare equation A and B right hand side parts. So what is S2 minus S1? It is Cv ln T2 by T1. And what is S3 minus S2? It is above equation B, that is Cv ln T1 by T2 plus R ln V3 by V2. Okay, R ln V3 by V2. Clear? This also can be written as T1 by T2 can be written as T2 by T1. And just you need a minus sign here. So it can be written as T2 by T1. Okay, and if you transpose this on the left hand side, it will be 2 times Cv ln T2 by T1. Okay, 2 times Cv ln T2 by T1 is equal to R ln V3 by V2. V3 by V2. Okay. Also, you know that the process is polytropic. So T2 by T3 can be written as V3 by V2 to the power of n minus 1. Okay, we have proved this thing for adiabatic case. So instead of gamma, you write n there. Okay. So what do I mean here is that since T2 by T3 is V3 by V2 to the power of n minus 1. because 2 to the 3 process is polytropic, not adiabatic. So this implies V3 by V2 is nothing but T2 by T3 to the power of 1 by n minus 1. Now put this V3 by V2 here, okay? So this will be 2 times CV ln T2 by T1 is equal to R ln T2 by T3 to the power of 1 over n minus 1. And T3 is again T1 only. So you can write this T3 as T1. Okay, it's given since T1 and T3 are same. Okay. Now, what is CV? We know that CV is R over gamma minus 1. We have proved this thing also earlier. So for an ideal gas. We have proved that time. So R over gamma minus 1. CV is R over gamma minus 1 ln times T2 by T1 is equal to R ln T2 by T1 to the power of 1 by n minus 1. Okay. Now R and R cancels out. Okay. And put this in the exponent ln T2 by T1 is 2 to the power of gamma minus 1 is equal to ln T2 by T1 to the power 1 by n minus 1. If you see, both the terms are equal, but you have to equate their exponents will be equal. Okay, then you can easily equate their exponents. That is, therefore, 2 to the power of gamma minus 1 is equal to 1 to the power of n minus 1. Now n minus 1 is gamma minus 1 by 2. So n is gamma minus 1 by 2 plus 1. So that is gamma minus 1 plus 2 by 2. So n comes out to be gamma plus 1 by 2. Final expression that was required. This is your answer. All right. So n is equal to gamma plus 1 by 2. It's a good question. Excellent question. Again, I'll explain in one go what happened. So we had two processes. First process was volume is equal to constant. Use the equation TdS is equal to Tu plus PdV. Okay. Put this dV will be 0 in this. So TdS is CV dt. Okay. So ds comes out to be CV dt by t. You can integrate from process 1 to 2. So 1 to 2 ds is equal to CV 1 to 2 dt by t integration. So S2 minus S1 is equal to CV ln T2 by T. We get that. Okay. This is our equation. Now let's come to again process 2 to 3. Okay. Process 2 to 3. So I'll write here like this. So this process is 1 to 2. This process is 2 to 3. Okay. This process is 2 to 3. Now, 2 to 3. You put TdS is equal to du plus PdV. So transpose T on the right hand side and write P by T as R by V. So ds comes out to be this. So integrate from 2 to 3 for the process. So it's S3 minus S2 CV ln T1 by T3 by T2, but T1 and T3 are same. It's given in the question that initial and final temperature are same. So it's R ln V3 by V2. You get that expression B as well. Okay. All right. So equation B comes out, and it is said that these are the expressions for entropies. Entropy change for both the processes are equal. So S2 minus S1 is S3 minus S2. Compare both of them. So it's 2 times CV ln. So it's CV ln T2 by T1 is equal to minus. Why minus? Because earlier it was T1 by T2 here. Oh, earlier it was T1 by T2 here. I've written T2 by T1 with a minus sign. Okay. So you transpose this on the left hand side, you get 2 times CV ln T2 by T1 R ln V3 by V2. Now you can write since you know from this expression T2 by T3 is equal to V3 by V2 power n minus 1. So V3 by V2 comes out and you put this expression V3 by V2 here. Okay. So you get the expression 2 times CV ln T2 by T1 is equal to R ln T2 by T1 power 1 by n minus 1. Okay. So here it was T3. So here T1 and T3 are same. That's why I've written like this. Now CV can be written as R upon gamma minus 1. So R and R cancel out. You are left with these two. Okay. Both the base are same for the log. Exponents can be compared. 2 power gamma minus 1 is equal to 1 by n minus 1. From here, after solving, n comes out to be gamma plus 1 by 2. Okay, that was required. Polytropic index in terms of adiabatic index. Okay, good question. All right, let's come to the another question. So all these questions which I'm taking are from a standard, very standard references. Okay, so make sure all these questions are very standard reference questions. You can find these questions. All right, next question. A gas or base equation P times V minus B is equal to RT, where V is constant. Instead, PV is equal to RT. Gas is obeying. It's not an ideal gas then. It's P into V minus B is equal to RT. B is constant and internal energy of gas follows equation U is equal to CV times T plus constant. Okay. Now for reversible adiabatic process, executed by this gas, you need to prove P into V minus B to the power of gamma is equal to constant. Okay, you need to prove this. This is not an ideal gas, but you need to prove PV raised by gamma is equal to constant. It's P into V minus B to the power of gamma is equal to constant. You need to prove that. It's a pretty simple question, not that too much hard. Take your time and solve. Okay, I guess in few of you have done. Let's start discussing this question. Okay, pretty simple question. So there is a gas which is obeying the law of P into V minus B is equal to RT, and B is constant here, and internal energy is given as function of temperature CVT plus some constant is there. And you need to prove for a reversible adiabatic process executed by this gas, expression P into V minus B to the power of gamma is constant. Let's prove. Let's do solution. Since for reversible adiabatic entropy changes 0. Okay. So we know the equation TdS is equal to du plus PdV. So it is 0 is equal to du plus PdV. Okay. This is our equation. All right. Now, since U is given as Cv times T plus constant. So what will be du? It is Cv dt plus 0 because differentiation of constant is 0. Okay. So this is your Tu. All right. So put this du here. You put this here. So Cv dt plus PdV is equal to 0. Okay. So Cv dt is equal to negative of PdV. Now you know that since PV is equal to RT, so P by T is equal to R by V. Okay. For idle gas. Okay. But this is not an ideal gas. So this is strong. Okay. So what is the expression here? Since it is given in the expression P gas is obeying P into V minus B is equal to RT. Since P into V minus B is equal to RT, so P by T is equal to TR by V minus B. All right. Or let's do. Let's do one thing. First, let us divide here both sides by T. dt by T is equal to minus P by T dV. Now let's write that expression. Since P into V minus B is equal to given as RT. So P by T is R upon V minus B. Now you put this P by T here. Therefore, Cv dt by T is equal to R upon V minus B dV. Now you can integrate. So it is Cv integration dt by T is equal to, but is Cv into T. Okay. Cv, yeah. Cv dt by T, R is constant, dV over V minus B. Now what is integration of dt by T? It is ln T. One thing, Cv can be written as R over gamma minus 1. For an ideal gas, we you know that. No, not for an ideal gas, for any gas. R is dependent on that gas. Okay, Cv can be written as R over gamma minus 1. V minus B. So this R and R cancel out. Okay. So this is 1 by gamma minus 1 integration of dt by t integration of dv by v minus b. Okay, now you can integrate. So this can be written as 1 by gamma minus 1 ln of t, and this can be written as ln of v minus b. Okay, ln of v minus b plus some constant will also come in integration, ln of c. Let's write that. Okay, take this on the exponent side, it will be ln of t to the power of 1 by gamma minus 1. Okay, is equal to ln of v minus b, ln of v minus b, and here r will also be there. Okay, because r was disposed of from here, but some r will be there as well. Okay, or what we can do, instead of expanding it here for non-confusions, instead of expanding it here, let's do one thing. Let's remove this so that there are no confusions. First integrate. So this is CV only. So again, this also to be removed. Let's integrate here only. So it is CV ln of t r ln of v minus b plus ln of c. Okay. Now you can write as r over gamma minus 1 ln of t is equal to r over r into ln of v minus b plus ln of c. Now you divide by r both sides. It will be 1 by gamma minus 1 ln of t. It will be ln of v minus b plus r ln of c. Okay, plus r ln of c. So was it negative of r? Am I making any mistake? Okay, so I made one mistake. Here it was minus p by t. So minus p by t, where it's gone. Here it was minus p by t. Okay, so I have to write minus r by v minus b. Minus sign I have missed, sorry. Okay, is it fine? Minus sign is back. So thank you for telling. ln of t, take the exponent 1 by gamma minus 1 is equal to ln of negative of ln of v minus b plus r ln c. So it can be again written as ln of t to the power of 1 gamma minus 1. It can be written as r ln c by v minus b. Okay, r ln c by v minus b. Okay, any doubts till here? If you have any doubts, please ask. So again, either you write r times ln of c, it's again a constant only. That's why I wrote in another form as well. Okay, so there is no confusion. So again, it can be written as capital C or whatever C you want. Okay, again, it can be removed. So it's again ln of c. Now you can compare that t to the power of 1 by gamma minus 1 is c by v minus b. Okay, c by v minus b. Multiply here t to the power of 1 by gamma minus 1 into v minus b is equal to c. Okay, is equal to c. Any doubts still here? So again, it can be written as t to the power of t into v minus b to the power of gamma minus 1 is equal to c to the power of gamma minus 1, that is c only. Okay, that is c only, and c is nothing but rt. Can I write like that? So that this exponent's gamma minus 1 gets removed. How can you remove this constant? Okay, t into v minus b the power of gamma divided by v minus b is equal to constant. Okay, can I write like this or not? Or let us do one other thing. It's given that since gas follows PV minus V to the power of gamma is equal to RT. Is it fine? This is given in the question. PV into V minus B is equal to RT. Why I'm writing this? Okay, is equal to RT. Is it fine? Is RT. Now, can you put T here? Can you like write this as V minus B to the power of gamma minus 1 is equal to constant? Can you write like this? If you multiply with V to the power of V minus B to the power of gamma minus 1 both the sides, can you write like this? Okay. If you multiply V minus B to the power of gamma minus 1 both the sides, RT into V minus B to the power of gamma minus 1 multiplied. This term has been multiplied on both the side of this. Okay. Now you know that this term is nothing but constant. Okay. So, and if you multiply V minus B to the power of left hand side, it can be written as V minus B to the power of 1 plus gamma minus 1 is equal to constant. So 1 and 1 cancel out. So it is P into V minus B to the power of gamma is equal to constant. That was required to be proved. Okay, a very good question again. So again, I'll explain once for all. So for a reversible adiabatic process, entropy is 0. You put TdS is equal to du plus PdV. Okay, in that this is 0, d is equal to du plus PdV. You know that CVT plus constant. So du will be CVDT plus 0 because u is not, it's not an ideal gas. You write like this. Okay. Now put this du here. Okay. Oh. You get your expression CVDT plus PdV is equal to 0. Transpose is on the right hand side. That is, and you can write P into V minus B is equal to RT. So P by T ratio is R by V minus B. You put the arc here. So you get the equation CVDT is equal to minus R by V minus BT. You can integrate now. On integration, you get CV ln T minus R ln V minus B ln C. Okay, CV is nothing but R over gamma minus 1 for a gas. So it's like this. Now as R ln C can be again written as capital R. Okay, or capital C or whatever C you want. It's again a constant only. So you get an expression that is T to the power ln of T to the power 1 by gamma minus 1 is ln C by V minus B. So having the same values, you get the expression T to the power of V minus B gamma minus 1 is equal to constant. Now it's given in the expression that, in the question that the gas follows this. So multiply V minus B to the power of gamma minus 1 both the sides. And you know that this term is nothing but constant, equal to constant. So left hand side is P to the power of V minus B to the power of gamma is equal to constant. Okay, pretty simple question, but a tricky one. Okay, I hope we did a lot of questions today, depth questions and very good questions. So if do you have any doubts for the session? No doubts? Great. So if no doubts are there, so we'll do very good questions again in the next tutorial as well. Okay, questions will be continued. I feel a lot of questions left to discuss. Okay, so I hope you guys are regular with your lecture videos, and those who have missed the tutorials can watch in the recordings. So those who have enrolled in the NPTEL course, they can watch. They are getting the sheet, recording sheets where all the links are there, as well as this PDF notes will be uploaded in that on the drive. And those who are first time watching this videos on, so this is my YouTube channel. You can watch all the videos at my YouTube channel, So YouTube, all the videos are here. NPTEL with Varnit. Okay, this is my YouTube channel, and in the video description, the link for the tribe will be there where you can see all these PDFs for every week. Okay, so I'll see you in the next week. All right, bye. Thank you.